Welcome to the Deep Dive, where we transform complex information into clear, compelling insights tailored just for you. Today, we're embarking on a really fascinating journey into the world of artificial intelligence, specifically a groundbreaking advancement in computer vision. Our mission for this deep dive is essentially to shortcut your way to being well-informed about a new technical report titled DINOv3. This work introduces a versatile vision foundation model that promises to fundamentally change how we approach visual representation learning.
That's right. This deep dive is really all about understanding DINOv3. It's a major milestone in self-supervised learning. The aim here is pretty ambitious: to virtually eliminate the need for manual data annotation. And this allows models to scale effortlessly to, massive data sets and larger, more powerful architectures. So we'll explore how DINOv3 achieves this, what makes its learned features genuinely superior, and critically, how it delivers state-of-the-art performance across a vast range of vision tasks without needing task-specific fine-tuning.
Okay, so for those of you already tracking the, let's say, incredible progress in self-supervised learning, why is this approach so crucial for computer vision right now? And how is DINOv3 really pushing the edge of what's possible here?
Well, self-supervised learning is so powerful because it fundamentally shifts how AI models learn. It's quite different. Instead of relying on painstakingly human-labeled data, it learns directly from the raw pixel data itself, leveraging the inherent patterns and structures within images. This really opens the door to training on virtually unlimited raw image collections. Huge potential there. DINOv3 represents a significant leap forward in that direction, aiming to be a truly versatile vision foundation model. It seeks to achieve state-of-the-art performance across highly diverse settings and, as you mentioned, a key breakthrough is doing so without requiring any additional task-specific fine-tuning.
So what this really means for us then is the promise of a single, highly reusable model, one that can generalize across an enormous range of tasks and domains. The report outlines DINOv3's three ambitious core objectives. First, create a genuinely versatile foundational model. Second, significantly improve what are known as dense features. These are crucial for detailed understanding, right?
Exactly. Things like segmentation need that detail.
And third, to make an entire family of these powerful models readily available and practical for deployment. That sounds incredibly ambitious, especially when you consider the scale involved. How did the researchers manage to achieve these objectives? The report points to leveraging surprisingly simple yet remarkably effective strategies. Let's start with scaling. How did DINOv3 tackle the immense challenges of using massive data sets and building models with, billions of parameters?
Right, scaling self-supervised learning models truly poses unique hurdles. It's not just about getting more data. It's about effectively collecting useful information from unlabeled sources. That's tricky. And then, critically, managing something called feature degradation during very long training periods. Features can kind of blur over time. DINOv3 addressed this through incredibly careful data preparation, thoughtful design, and optimization. They began with a staggering pool of 17 billion web images, just a massive amount. But it wasn't just raw collection. They applied sophisticated automatic curation methods like hierarchical k-means for clustering and retrieval-based systems to identify relevant images. Then, they mixed this web data with specialized high-quality datasets like ImageNet 1K, and the study showed this mixed approach consistently yielded better results than any single curation method alone. It proved the immense benefit of such diverse yet carefully managed data.
So collecting and curating that vast data set is clearly, a Herculean task in itself. But even with perfect data, doesn't scaling the model itself to something as immense as a 7 billion parameter vision transformer introduce entirely new headaches? Specifically, you mentioned feature degradation. What exactly is going wrong under the hood when these models get so big, and how did DINOv3 prevent that?
You've hit on a really critical point there. While global performance, things like image classification, generally improved with longer training and bigger models, they observed a subtle yet significant problem. The quality of dense feature maps actually degraded. And these dense features are absolutely crucial for tasks demanding fine-grained detail, like segmenting specific objects or accurately estimating depth. This degradation manifested as a loss of patch-level consistency. Basically, similarity maps between image patches became increasingly noisy and less coherent over time. You can actually see this visually represented in the report's Figure 5a. The details just get fuzzier. Their solution is quite clever, actually. It's a new method called gram anchoring. Think of it as a sophisticated quality control system for how the model perceives details. Instead of trying to fix individual features directly, it regularizes the gram matrix. Now, For those unfamiliar, you can imagine a gram matrix as a unique fingerprint of how all the different visual elements in an image relate to each other. It captures style and texture relationships across patches. By continuously pushing the student model's gram matrix towards that of an earlier, more stable gram teacher, they effectively mitigate this degradation. This ensures that even as the model scales, this visual coherence, the quality of its fine-grained features, remains stable and clean. It essentially eliminated a critical bottleneck that had plagued previous attempts at massive self-supervised vision models.
That's a fascinating approach. So it's not about micromanaging every single detail, but ensuring the overall style, the coherence of feature relationships, stays robust. And the report also mentions leveraging higher resolution features for this gram anchoring. What was the impact of that specific technique?
Oh, the impact was significant and remarkably immediate. Integrating gram anchoring led to substantial improvements on those dense tasks we discussed. For instance, a really notable gain on the 80-20K semantic segmentation benchmark. This means the model became dramatically better at precisely outlining and understanding every object in a scene. That's essential for things like medical imaging or autonomous driving, right? It essentially repairs those degraded local features, even when applied later in the training process. And the clever addition of using high-resolution features for the gram teacher, that involved inputting images at twice the normal resolution, then downsampling the feature maps. This preserved superior patch-level consistency and further refined the dense task predictions. It gave them additional crucial gains in detail and accuracy.
Okay, so we've established how DINOv3 maintains its incredible feature quality even at massive scale. That gram anchoring seems key. But once you have this powerful, high-fidelity model, how do you make it practically useful, across a diverse range of real-world scenarios? This brings us to DINOv3's post-hoc strategies. What are these, and how do they boost the model's flexibility and deployability?
Right. These strategies are all about making the model truly adaptable and ready for practical use. Different applications, different compute budgets. First, they implemented resolution scaling. Most models train at a fixed resolution, but the real world has everything from tiny 8.0 thumbnails to ultra-high-definition 4K feeds. Resolution scaling adapts DINOv3 to process images effectively at various input resolutions, even very high ones up to 4K and beyond, all while maintaining stable feature maps. And gram anchoring was essential during this adaptation phase, too, to prevent quality loss at new resolutions.
So it works reliably regardless of the input camera, basically.
Exactly. Very important for real-world use. Second, they employed model distillation. While the 7 billion parameter model is incredibly powerful, it's often just too massive for many applications or devices with limited resources. Distillation allows them to transfer the vast knowledge from this gargantuan model into smaller, more efficient variants. Things like Vision Transformer Small, Base, and Large, and even context-based architectures. This creates a versatile family of models, you can see it in Figure 16a, of the report deployable across a wide range of computational budgets. And the smaller models achieve performance remarkably close to the large teacher. It's like having a master chef train excellent sous chefs for different kitchens.
That makes it much more accessible.
Precisely. And third, they introduced text alignment. To move beyond pure visual understanding and connect it to human language, they aligned DINOv3 with a text encoder. This enables robust zero-shot capabilities, meaning the model can understand and respond to text prompts about images it hasn't explicitly seen labeled that way before. It effectively bridges visual features to text descriptions for even broader applicability, allowing for more intuitive human-AI interaction.
Okay, so we have a model that learns from vast unlabeled data, maintains high-quality features through clever techniques like gram anchoring, and then adapts to various practical needs through these post-hoc strategies like distillation and resolution scaling. This is really where DINOv3 proves its mettle, right? We're talking about a model learning from unlabeled data, yet delivering across a mind-boggling array of vision tasks. What does this actually translate to in terms of real-world performance? How well does it do?
Well, what's truly fascinating here is the sheer versatility and consistent excellence. It's quite remarkable. DINOv3 delivers exceptional performance across a broad spectrum of tasks, often outperforming specialized models without any task-specific fine-tuning. For those demanding dense tasks like semantic segmentation, DINOv3 surpassed previous self-supervised baselines by over 6 IOU points on the 80-20K dataset.
And 6 points in IOU is a huge jump in segmentation quality, isn't it?
It really is. It means the model is dramatically better at precisely outlining and understanding every object in a scene, critical for complex environments. It even outcompeted models distilled from heavily supervised approaches. On monocular depth estimation, it also set new state-of-the-art results, outperforming its predecessor, DINOv2, by a notable margin on Kitty. signifying more accurate 3D understanding from a single 2D image. The visualizations in their Figure 13 really show it. DINOv3's features are sharper, cleaner, semantically more coherent than other strong backbones. It's not just aesthetics, it's functional quality.
So it's not just recognizing objects, but understanding their boundaries, texture, relationships in 3D space with really remarkable precision. What about its ability to understand the broader image context or even video, not just static scenes?
Ah, yes. DINOv3 also excels at global image tasks, which involve understanding the overall content. On out-of-distribution classification benchmarks, like ImageNet A and ObjectNet, it achieves results comparable to or even exceeding the strongest weakly supervised models. This is important because it shows DINOv3 is highly robust. It performs well even on images significantly different from its training data. Crucial for real-world reliability. It also set new benchmarks for fine-grained classification and instance recognition. Big improvements over DINOv2 on datasets like MET and Amsterdam.
Demonstrating it can discern subtle differences between very similar objects.
Exactly. That fine-grained ability is impressive. Furthermore, its features demonstrated a strong temporal consistency for video segmentation tracking. This is particularly striking because DINOv3 was not explicitly trained on video data. Yet it outperformed competitors on datasets like Datas by a significant margin over DINO2. This inherent stability of its features across frames makes it an excellent foundation for a wide array of video applications without needing specific video training beforehand.
That makes sense. It sounds like DINOv3 can serve as an incredibly robust and versatile foundation for building more complex vision systems. When we say frozen backbone, just to clarify for listeners, imagine DINOv3 as this highly skilled foundation artist, right? We've trained it to be an incredible generalist, and now for specialized tasks like object detection, we just freeze its core capabilities and add a small task-specific layer on top. It saves massive computational resources. So how does this foundation artist perform when combined with other tools? And are there any specific limitations that emerge at this scale?
It performs exceptionally well, often setting new benchmarks. When DINOv3 is used as that frozen backbone in systems for, say, object detection with plain DTR, it achieves state-of-the-art performance on COCO, outperforming models with significantly more trainable parameters. That highlights its efficiency. For semantic segmentation with mask-2 former, it equals previous state-of-the-art on 8020K while keeping the backbone frozen, again showing its strength as a pre-trained generalist. It even sets new state-of-the-art results for monocular depth estimation and 3D understanding when plugged into the VGGT pipeline, replacing DINOv2 and giving clear gains. Now, regarding limitations. While the smaller distilled models are highly efficient for deployment, you have to remember the initial training. Training that 7 billion parameter DINOv3 model on 17 billion images requires, well, immense computational resources. This scale, while yielding incredible results, can definitely be a barrier for smaller labs or independent researchers without access to that kind of infrastructure. However, the release of the model family aims to mitigate this by providing accessible, high-performing variants for practical use.
Right, that initial cost is huge, but the distilled models bring the power down to more manageable levels. That's an important point about balancing cost and efficiency. And to top it all off, the report even shows its application to highly specialized domains, like geospatial data. That seems quite far removed from typical web images.
That's right, and it truly showcases the generality of the DINOv3 training recipe. It's not just for cat photos. They pre-trained a DINOv3 model specifically on 493 million satellite images, creating DINOv3 SAT. This specialized model achieves state-of-the-art performance for canopy height estimation from space, and it set new benchmarks on an impressive 12 out of 15 geobench tasks. What's even more striking is it often outperformed other models that utilize more input channels than just standard RGB, proving its effectiveness and versatility across really diverse image domains.
Wow. This deep dive into DINOv3 truly showcases the immense power of self-supervised learning when scaled effectively and thoughtfully. By ingeniously addressing challenges like data curation at massive scale, overcoming feature degradation with that elegant Graham anchoring technique, and ensuring practical deployment with robust distillation and resolution scaling, DINOv3 really does offer a remarkable leap forward, creating adaptable and incredibly high-performing vision models.
It undeniably highlights that with careful design and optimization, models can learn incredibly rich and versatile visual representations directly from raw, unlabeled images. This is setting new standards across almost every computer vision task we've looked at today. The consistency and quality of its dense features, coupled with its broad applicability and efficiency through distillation, those are particularly impressive achievements, I think.
So as we consider DINOv3's ability to learn from vast unlabeled data and then deliver state-of-the-art results across such a wide array of vision tasks, it really makes you wonder, doesn't it? What entirely new visual intelligence applications might become possible when the barrier of manual data annotation is virtually removed? When, every camera feed and image repository on Earth could potentially inform these powerful models? What previously unseeable patterns might emerge? What complex visual insights could AI uncover in fields we haven't even thought to apply it to yet? Just something to think about. Thank you for joining us on this deep dive into DINOv3. We hope you feel well informed and perhaps a little inspired by the future of computer vision. Until next time.